Hi there, and welcome to the DynamoDB corner of the Amazon Web Services YouTube channel. I'm your host, Sean, and I'm a DynamoDB Specialist Solutions Architect. I'm coming to you from my office in Dallas, Texas, and as I record this, it is summertime. It is heating up out there, but speaking of heat, part of this presentation covers how to manage partition heat driven by uneven access patterns, among many other topics. This is part one of a two-part series of the operational best practices for DynamoDB, distilling my decade of experience supporting DynamoDB into about an hour of content. Free of charge, of course. Now, after you're done with this video, watch part two. Let's get this presentation started. Sean?
I've already told you about myself, so without further ado, let's hop into our presentation. We're covering a lot of great things. I think this is one of the better presentations that I've made in terms of the breadth and the depth that we will be covering. Some of our presentations are just about access patterns and schema designs, as some of our talks are going to be about really small things like account limits. And this presentation does all of that. We cover access patterns, we cover your account limits, we cover quotas, transaction streams, indexes. If the feature exists in DynamoDB, we will probably mention it, and there's a good chance that we will dig in deep and discuss some important things to know. If you're going to watch one presentation, aside from the NoSQL designs, like the design patterns presentation, you need to watch this one, and we're going to cover a lot of really important things, and you need to know about DynamoDB. So let us begin by discussing the DynamoDB service. Now, the expectation for this presentation is that you have a background in DynamoDB. This presentation, I would say, is probably about the 300 to 400 level. If you don't know what DynamoDB is, then I would pause this, stop this, go back and watch DynamoDB history and how it works, which is another presentation in this series, because we're going to expect that you know about partition keys, that see what a GSI is, why you would pick a GSI versus an LSI. We're also going to expect that you know what a capacity unit is, because we won't be going into too much depth. Now, that being said, we will cover a couple of the basics here just to get us started in case, you're being forced to watch this presentation and you don't want to be completely lost. You don't have time to go back to the other one. Maybe you're about to go live. You have a launch date coming up, and you're like, I need this information now. Fine. And twisted my wrist. I will go ahead and cover DynamoDB in a nutshell. So the DynamoDB service is, a fully managed NoSQL database service running on SSDs in 3 different availability zones. When you go to your account, you create what's called a table. A table has items. Underneath the surface, that table sits on partitions. Partitions are spread across 3 different availability zones. So in the case of an on-demand table, if you make an on-demand table, you're going to have a table that you see with a specific table name. Underneath the surface, there is 4 partitions for those. Each partition's data is duplicated across 3 different availability zones. For that reason, DynamoDB provides a 4 nines availability SLA, which is available on our website at aws.amazon.com/DynamoDB/SLA. Now, in the event that you do need higher availability, most likely it's not an issue at Dynamo why you would leave a region, evacuate a region, and go to another region. If you need that, then we have global tables, which we'll talk about next. Let's talk about how you access DynamoDB. So you are you're a Java application. Like Java bytecode, the JVM. I don't know. I'm not a Java programmer. I'm a Python person. I could make so many more Python jokes. But let's say you're a Java application. You sit in a Linux computer. You import the Java SDK. And inside the Java SDK is a DynamoDB client. And there's Java SDK v1, v2. You can pick your version. You can go with the DynamoDB modeler, which is a high-level client. Or in v2, the version of the modeler is called the enhanced client. Long story short, Dynamo client, you want to access your data in DynamoDB. How do you do that? Well, you tell us what the region is, such as US East 1, and then the client will go and resolve a domain name using the DNS system. The domain name is something like dynamodb.useast1.amazonaws.com. When that is resolved, we return back an IP address with a TTL of 5 seconds. A single IP address is a public IP. DynamoDB is a public web service. It is fronted and secured through IAM policies, primarily identity policies. But with those IP addresses, you are able to interact with us. And you can connect over TCP or you use TCP, but you can connect in either plain text on port 80 or using TLS over 443. So you have your choice of how to connect to DynamoDB. Once you establish your connection, what you're doing is actually talking to the front end of DynamoDB through a load balancer technically, but it's what's called a request router, and behind the request router is the storage nodes. Effectively, DynamoDB is a two-tier service. Request routers on the front end, storage nodes in the back end, RR, SN. SNs are the ones that hold your partition data. We hold your data in 3 different availability zones. So DynamoDB in a nutshell is a fully managed NoSQL database service that is replicated into 3 different availability zones. We offer single-digit millisecond latency. We're secured by IAM. You connect to us over these IP addresses. Use those IAM credentials based on what kind of permissions you have, which we'll dig in later, and you can access our service. And when you do your puts and gets and all that, you're talking with individual DynamoDB partitions in most cases. Now, let's say you have a requirement of having high availability. Let's discuss that. And at the very end of this section, we'll kind of cover some important things to know about configuring your SDKs. So with DynamoDB, we have an offering called Global Tables. Global Tables is our fully managed multi-leader database service. It's essentially tying together multiple regional DynamoDB tables. You still do everything you did in the previous slide. You do your puts and gets and queries and everything on DynamoDB in the region. And then what Global Tables does underneath the service is string these tables together. So if you put an item into DynamoDB in region 1, we have a log processor to pull those records out and push them into region 2. If you make a write an item in region 2, we will replicate that back to region 1. The Global Tables service is an anti-entropy system at its core. Its goal is to make all the items in all the regions look exactly the same. Now, when we compare items in order to figure out which should be maintained or retained, we use a timestamp. The timestamp is added at the storage layer. In the latest version of Global Tables 2019-11-21, which is a date, aka Global Tables version 2, the timestamp is added at the storage layer and it is transparent to you, meaning you can't see it. And this strategy of conflict resolution is called last writer wins. So from an operational standpoint, the thing that you need to consider is whenever you are writing an item in, Global Tables is going to figure out which item to keep. If you do 2 writes at the same time, that can be an issue because it's not easy to figure out which item won. It's not like we report, oh, there was a conflict. This was the old message. This is the new message, the new item, old item, and let you figure it out. That's not really how it works. So there's important things I can point out here while we're here. The default version of Global Tables is Global Tables 2019. We'll discuss that in a little bit, and that's the version that we kind of expect you to be using moving forward. There are some CloudWatch metrics that you can use to monitor replication latency, which we'll discuss in the next slide. The service, Global Tables, is modified, if you're creating these tables, modifying them, using the traditional update table, create table API operations. This is Global Tables 2019. Now, there are some old API operations that have Global Tables in the name. If you are making any API call to DynamoDB and Global Table is in the API operation name, you're using the old version of Global Tables. Those do not apply. We are using the latest version of Global Tables, which uses update table and create table. Now, Global Tables is often used in the case of DR, and our customers will run multiple replicas, multiple copies of the table in different regions. Now, in order to speed up this replication and also allow for independent isolation of specific regions, the replication system is working in parallel. So from region 1, we have a log processor sending to region 2 and a separate system sending to region 3. There's no dependencies. So this means, of course, obviously the DynamoDB table needs to exist, but assuming the DynamoDB table has not been deleted by you, we will be able to replicate it to the remote regions. And in doing so, we're going to publish CloudWatch metrics. We'll talk about those in a little bit. So if there's an impact on region 2 and there's some kind of errors coming back from DynamoDB in that region, which is extremely rare that that happens, but in any case, all it will mean is replication will slow down. Now, something you need to know is that if you disable an AWS region, or if you make the encryption key for that replica inaccessible, and by disabling the region, you're opting out, or by, if you're, making the key inaccessible to DynamoDB, you're saying, hey, I want no one to be able to access this data. I want to burn it. After about 20 hours, DynamoDB will remove that replica from the replication group. So if region 2 is opted out, if you can do that, or if you change the key, it will be removed. And then the thing is, though, if it's within that 20 hours, you all of a sudden give us the grants back, or the region is now available, we will start replaying changes into region 2. And I should also add that what global tables will do in the background is, our goal is to make every item exactly the same. We will periodically check the items and make sure that item, with partition key user number 1 is the same in all the regions. We have a system that works in the background to resolve any kind of potential conflicts or any of that, because we want every item to be exactly the same in global tables. Now, here's the best practice. You need to monitor this replication metric called replication latency. This is the only metric that we publish for Global Tables 2019, aka GTV2. The metric name is replication latency. The dimensions are table name and receiving region. We want you to monitor that because it's going to tell you what the speed of the replication latency is between region 1 and region 2. Now, if you ask us, hey, how long should this be? We're going to say, it's 2 to 3 seconds. That's just the off-the-cuff default answer of how long it should take to replicate data between 2 regions, but it's dependent on your provision capacity in the remote region. If you're using the provision mode, it also depends on the geographical distance between the 2 regions, potentially a little bit of network traffic. And then, of course, it's also going to depend on what your provision capacity is in the remote region. If you are updating your Dynamo global tables with new capacity settings, you should be using the update table APIs. We will maintain the application auto-scaling settings for you if you're using the provision mode, making sure that the global secondary index and the base table all have the right settings. That being said, in Global Tables 2019, the write capacity on the base table and on the GSIs need to be the same. This is enforced. Now, in the remote regions, and I think in all the regions, you can change the read capacity settings, so those can be independent. But the write capacity does need to be the same. We need to make sure that 100% of the items in the base table in region 1 can be replicated into region 2's base table, as well as can be replicated into region 2's global secondary index. Not to mention region 1's global secondary index, which needs to have the same definition. At the end of the day, we put some guardrails on Global Tables 2019. We want to make sure data can be written. It can be written quickly. We want to make sure all the items are exactly the same. In the provision throughput model, or for that matter, for the on-demand model, this means making sure there's sufficient capacity, sufficient partitions to allow the data to be written. Now, we recommend to use GT 2019. That is the default in the console. It uses fewer replicated write capacity units, which, by the way, is a different capacity unit than a regional table. So base tables that are only in one region use write capacity units or write units. Their GSIs will use write capacity units. But the base tables and global secondary indexes uses replicate write capacity units, which are charged at a higher rate, so be aware of that. So anyways, when we're using it, we know that replicate write capacity units are going to be used for replication. GT 2019 uses fewer of them because it doesn't have what's called a write expansion factor, which was common with GT 2017. So please use it. It will be cheaper. Now, if you're on the old version, you can migrate. We have documentation on that, which discusses the changes to the stream records. Be aware of that. Monitor the replication latency. You can look at average, minimum, and maximum. I would say the truth is maximum is good to know, but it can be really skewed. If you're going to set an alarm on average replication latency between US East 1 and US West 2, for example. The way this metric looks is you connect to CloudWatch in US East 1, and to see the replication latency from, meaning in one direction, from US East 1 to US West 2, you look where the table name is equal to whatever it is, and then the receiving region is equal to US West 2, and you're calling CloudWatch in US East 1, and in that way you'll see the one-way replication latency. Now, obviously, you have to know what the other side of the replication latency is, and so then you have to set up alarms and dashboarding and whatever in the other region. So be aware of that. Now, with Global Tables 2019, unlike 2017, you can add regions at any time. There's customers ask if there's any considerations, and the answer is really not. There's nothing to consider other than account limits. Account limits are tricky, but you're not going to have any kind of performance impact upgrading to a new version of Global Tables, or sorry, adding a new region to Global Tables in GT 2019. You're not going to have any kind of like performance impacts. Now, your account limits in Global Tables, there's a few of them that must be synchronized, and you must do this in order. Order matters. The first thing you need to do is request a change to the max streams IOPS limit, also known as, in the Service Console, write throughput limit for DynamoDB streams in provisioned mode. This limit must always be higher than your table write throughput limit. So when you're adding a replica to a new region or you're making a global table spanning multiple regions, if you have non-default limits, if at any time your write capacity, meaning your table write throughput limit, which is normally 40,000 units, if it has been raised, you need to get the max streams ops limit raised first to that level or above that level. Only when that is done, you follow up with the second support case, or really make something to service quotas, and request that the table write throughput limit be increased. Those must be done in exactly that order, otherwise you'll receive errors, so please follow this guidance. Now, once you have the max streams IOPS limit set, as well as the table write throughput limit in every region, and they all must all be the same, hence they must be equal at the top, or syncing limits, or syncing across regions, ask AWS support to check the other limits. And there's a couple of them called allow large index, allow large stream, allow add replica size limit, max streams partition limit. You can just say, hey, check like the first two of these, allow large index, allow large stream. If you've ever had these increased, you probably know. You must be a very large customer with thousands of partitions in a single table for those limits to apply. But do ask that they check those, because if you're adding a replica in a remote region, and let's say it's a table that's 20 terabytes, that may hit certain limits, and you'll find those when you update the table to add the new region. But it would be better to have those set in advance. And if you have enterprise support, work with your enterprise support technical account manager and the account team to assist you with those limit changes. Let's also talk about how to manage the table with CloudFormation. So with AWS CloudFormation, whenever you are converting a regional table to a global table, you can do that, but it has to be done outside of CloudFormation. So you have to go to the management console for DynamoDB, upgrade the regional table to a global table, and then once it's a global table, you can import it back into CloudFormation using the global table resource. Those are two separate resources in CloudFormation, the DynamoDB table versus the global table. So be aware of that technique. Remove it from the stack, modify it, bring it back into the stack. Of course, if it's already a global table in your CloudFormation template, you can simply add a new region replica to there, and then it will add the replica via the DynamoDB APIs. The last thing that I would say is that TTL is not for you with global tables. When you write data into DynamoDB, you can add the TTL attribute, which is an epoch timestamp, the number of seconds since Jan 1, 1970. After that point, the item will be deleted at some point. There's no guarantee, or it will be deleted, but there's no SLA, I should say, on how long it'll take to delete. It could take an hour, it could take 2 days, could take 3 days. It varies. Now, as you recall, with global tables, the goal of the service is to make sure all the items look the same, which means if you delete an item in one region, it's going to immediately replicate to the remote regions. So if you have TTL enabled and an item expires in region 1, we will immediately replicate that right to region 2. Now, the original delete in region 1 is free. TTL deleted that's its value, that's the benefit. But because it's an immediate write, region 2 will have to pay replicated write capacity units to delete the item. So TTL is not free with global tables. The originating region of the TTL delete, that write is free, but then you have to pay to replicate the change. So be aware of that impact. As I mentioned earlier, consider enabling PITR, point-in-time recovery, on a global table, and really on any table for that matter, in order to durably maintain a backup of the table in Amazon S3. Depending on the option, you can do an on-demand backup, which stores the snapshot at a point in time with second granularity in the AWS, really Amazon S3 account that DynamoDB owns. In your account, it appears as a snapshot. You can see the source, the time, the table name, and all that, and then you can restore it at any point in the future, as long as you retain the snapshot. Now, the other way of backup data in DynamoDB is PITR, point-in-time recovery. Point-in-time recovery offers 35 days of retention with second granularity. No matter which way you choose to, quote-unquote, back up your table data, upon restore, it will be restored into a new Dynamo table. Now, on restore, you do get some options. You can choose whether to include the indexes or not. You can choose different capacity settings. The options are noted in our documentation as well as in our API docs. So not only our developer documentation, but our API documentation explaining which options are applied upon table restore. So if you have any questions, go ahead and review those. Now, I put the price chart up here, not because this is, comparing apples to apples. It's really more an apples to oranges kind of decision here between PITR and on-demand backups. Now, first, I should say you have two options for the on-demand backups. You can either use the DynamoDB backups using DynamoDB APIs, or you can use AWS backups with advanced backups. We'll talk more about the advanced backups with AWS backup in a little bit, but it gives you a lot more features, a lot more control. PITR, though, as of the time of this recording, strictly speaking, is just a DynamoDB construct. Now, these PITR backups can be cost effective. Kind of the point of this slide is to show you the relative cost, but also to get you to consider. If you made two warm on-demand snapshots, you're effectively at the same cost as PITR. And so if you just enable PITR and you need 35 days of retention, why not go with that and skip the snapshots? It can be much more cost effective. Now, there's some important things to consider. Usually if customers are using on-demand backups, it's because of compliance reasons. They need a snapshot of the table. They need to keep it for a year. Maybe they need to keep table data for 2 years. And there we go. On-demand backups come to play. There's also cold storage tier, but we'll talk more about that in a little bit. Now, I should discuss a little bit about gigabyte month and how this is all calculated. Essentially, whether it's on-demand backup or PITR, you're paying per gigabyte month. In the case of on-demand backups, you're paying for how much data you've backed up for every hour. So in each hour, we look at how much data is in a snapshot. We determine, based on the monthly cost, what that would be at the hour, because like a given month might have 730 hours. So we figure out, okay, if you just had that backup for one of 730 hours, what would that cost be? And then a detailed line item is dropped into your bill. The same is done with PITR. With PITR, we know approximately the size of your table at any point in time. And so for that month, with PITR enabled, we emit a data point saying, this is a 100 gigabyte table. This is just 1 hour of the 730. So we take whatever the rate card price would be, 20 cents per gigabyte per month. If it's like a 1 gigabyte table, we basically take 20 cents and we divide that by 730, which is the number of hours in your average month. And in doing so, we convert what's gigabyte month down to gigabyte hour. And now you know way more than you ever want to know about how we calculate our bills. Now, there's some wonky stuff that happens. There's some synthetic data points that pop into your bill. But rest assured, at the end of the month, whatever you are billed for your on-demand backup or PITR or your PITR feature is based on the average size of the table or the backup, and our system is quite resilient. Now, with advanced backups with AWS backups, you get access to tiered storage, which includes cold storage. As you saw in the previous slide, the cold storage is offered at a much lower cost. Now, the only limitation there is that any backups that are rotated from warm into cold storage must be retained for 90 days. Now, in your AWS bill, if you were to use on-demand backups, the service name where this usage comes from is Amazon DynamoDB, whereas with AWS Backup, the service name was going to be the AWS Backup Service. What I'm effectively saying is you have two different places, two different services that can back up your table data. Now, advanced backups offer a lot of cool things. You get cold storage, you can do cross-region and cross-account copy. That's great for migrating to a new AWS account. You can make an on-demand backup of a Dynamo table, copy that to the new account's vault, and restore it. You can make an on-demand backup of a table, copy that backup to remote region for your pilot light scenario where your data is there but nothing's on. You can just restore from backup. That's pretty amazing. You can also choose your own encryption key, but with DynamoDB on-demand backups, those encryption keys are per table, whereas with advanced backups in the AWS Backup Vault, it's at the vault level key. You can do cost allocation with AWS Backup, where you can add a tag, and then you can group all the costs for your production user application. If user was the name of your application, it's a production stage, you can put a tag on that. And then we can figure out, or you can figure out in your bill, what's the cost for a Dynamo table, what's the cost for the backups, all in one, and it wraps up real nice and easy. Now, finally, you can have a write once, read many option through the AWS Backup Vault lock. So if you have a compliance requirement, such as no one, not even me, not the root user, no one can delete the data for 1 year, that is possible through the AWS Backup Vault lock. Write backups in there. They are not coming out. Cannot be deleted no matter what. That's pretty cool. Now, as I promised, we're going to talk about some common considerations with AWS SDKs. Honestly, I couldn't figure out where else to put this in the presentation, but I'm like, availability, durability, yeah, this makes sense. Let's talk about SDKs. Now, this is a complex subject. Even if you look at like the Java SDK version 2, the latest version of that SDK, you might think, oh yeah, it's pretty easy to talk about the network configuration there. It is in fact not, because there's 4 different network clients depending on which APIs you're using. You can use the URL client, you can use the Netty IO. In case you're using like async, you're going to be using Netty. You can use Apache, and then I forget the 4th one, but yeah, many different options, many different clients to access DynamoDB underneath the hood, even though the top high-level SDK makes it look very simple. So here are some common things to consider. These terms like connect, read, TCP keep alive are generally consistent across different SDKs. Most SDKs will let you set these settings. Now, the first thing that we suggest is that you enable TCP keep alives. TCP keep alives keeps sockets open. So with DynamoDB, the connection setup is often the longest part of the initial connection. The more requests you can send through that TCP socket, that TCP connection, the better, regardless of whether it's TLS encrypted or not. The longer that connection is running, the better for you. Because you don't have to deal with connection setup. Now, when you're setting up that connection, there's something called a connect timeout. In the case of the Boto SDK, that defaults to 60 seconds. Connect timeout is the time it takes to establish a new connection. If your application is waiting a minute to establish a connection to DynamoDB, there's a serious issue. So you should be lowering that timeout to just a few seconds. And read timeout is the amount of time between when you send bytes until you get a response back on a socket. I believe technically that's correct, but the documentation can correct me. And so in the case of connect and read timeout, I want you to set that to a few seconds. Now, let's say you set TCP keep alive, you have some reasonable timeouts, and by the way, connect and read timeouts really aren't about the request timeouts. Connect and read timeouts are just about TCP socket stuff, how long it takes to set up, how long it takes to receive a response back, another packet back. Let's talk about more application level changes that you can make in your client code. Now, if you get an internal server error of 500, we want you to retry those as quickly as possible. 500 errors are transient. In general, in Dynamo will appear in a couple of seconds, will go away. They'll often come from a single partition in DynamoDB, not from the whole service. So we want you to retry those quickly. And so this may mean you disable retries, write your own logic, and if you see an internal server error, aka which is reported in CloudWatch, by the way, as a system error, you want to retry that quickly. Now, not as quickly as the aggressive retry strategies that we suggest for throttle responses, such as provision throughput exceeded exceptions. So when you are exhausting your provision capacity, some of these clients will default to sleeping 20 seconds at the most between retries, which is very, very slow. We want to see a much more aggressive retry with a sleep time, more like 100 milliseconds, 200 milliseconds, so you can quickly write the data into DynamoDB or read it out. Now, for latency issues, if you're seeing any latency, do these things. if you're on AWS Lambda, use AWS X-Ray, enable the tracing. You can use the Lambda Power Tools for your programming language if available. It allows you to quickly add X-Ray tracing and see what the latency is for accessing a service like DynamoDB. It also will record the request IDs. Now, in the event of just not having that option, you can look at enabling debug. So in Bodo 3, you would find the URL lib3 connection library, find that, and then mark it as debug, set the log level as debug. Or you can enable trace logging, such as in the event of the Java SDK, and that's going to help you monitor the connection pool. For latency issues, we're looking at maybe there's something wrong with the connection setup, so that's where debug and trace logging will come up, show you how long it takes to set up a TCP connection, the state of the pool. X-ray tracing will tell you the overall latency along with request ID, which is really important to trace things down on the DynamoDB service by AWS Premium Support. So that is a pretty detailed, complicated, but hopefully distilled, I don't know if those two words go together, explanation of how to configure SDKs. Enable TCP keep alive, set the connect and read timeouts to a couple of seconds, handle the retries correctly, and if you're having latency issues, just log, because the logs will help you determine kind of what the issue is. Let's discuss the considerations for event-driven programming on DynamoDB, as well as some things to know about adding global secondary indexes, a little bit about LSIs, kind of the comparison of the two, how do we monitor LSI collection size, and without further ado, let's hop in. Now, as I sat down to plan out what I would discuss on this slide, I first started creating a list of commonalities between the two streaming services that DynamoDB kind of supports that we publish records into, Kinesis Data Streams and DynamoDB Streams. After a lot of brainstorming, I realized that there actually are an incredible number of differences between these two options, and so I'm going to try to explain what they have in common, and then, hopefully give you some good things to know, best practices while you're working with them, things to monitor, and things like that. Now, no matter which option you choose, DynamoDB acts as a producer or publisher of records into the streaming service. All changes for a table, or quote-unquote all, appear in the stream for you to process. However, in the case of Kinesis Data Streams, records appear 0 or many times, which we'll explain in a little bit. A change is a create, update, or delete in a DynamoDB item that results in mutation. If you delete an item that never existed in the first place, or update an item, quote-unquote, and make no changes, a stream record is not created. Now, reads naturally do not create stream records because there's no mutation. These streaming services can be used for many things. For example, if you wanted to stream changes from one DynamoDB table to another, you could build your own replication service with one of these streaming services and AWS Lambda, writing items as they appear in the stream via the DynamoDB APIs. Here is where they begin to diverge. If you consider record ordering, maybe even records appearing, cost, management burden, SDK versions, and even retention time, there will be many differences between the services. DynamoDB Streams is fully managed, and there's no additional cost to use DynamoDB Streams for most customers. However, Kinesis Data Streams is not managed. You have to create the correct number of shards on the stream to match the throughput of your DynamoDB table. You have to pay Kinesis for every shard hour and for every put into the Kinesis Data Stream. With DynamoDB, you pay nothing to turn the service on. There's no cost for shards, and you pay only a small amount if you read the stream using the Kinesis Client Library, SDK. I should note that it is free to read a DynamoDB stream from AWS Lambda, which is why we say DynamoDB Streams is free for most customers, because you pay no cost to write the records into the stream with DynamoDB Streams. And if you read from Lambda, there's no associated DynamoDB cost, you just pay AWS Lambda. Now, an important distinction between the two options is that DynamoDB Streams maintains the order of an item based on the actual position of the record in DynamoDB's replication logs. But on the other hand, Kinesis Data Streams for DynamoDB can lose order due to the design of the Kinesis APIs that we use. I'm going to cover this in one more slide. So if you need strict ordering, it's better if you use the DynamoDB Stream service. Now, one less important difference is that DynamoDB Streams retains changes for 24 hours, but Kinesis Streams can retain data for a year if you're willing to pay for it. Now, at this point, you may be wondering, how do we pick between the two? Now, there are many good reasons why customers would use Kinesis Data Streams, and primarily is the entire ecosystem built around Kinesis Data Streams. You can connect a Kinesis Stream to Kinesis Data Analytics for streaming queries such as aggregations, or to Kinesis Data Firehose for replication into Amazon OpenSearch. That's just the tip of the iceberg. So in this slide, we show a Lambda function attached to the Kinesis data stream, and when configured, AWS Lambda begins to pull the Kinesis data stream once per second. It reads records that are added to the stream by the DynamoDB service. Now, I don't want to undersell the benefit that AWS Lambda provides. It maintains its cursor in the stream and it processes the retries for you. The AWS Lambda service ensures every record is given to the Lambda function at least once. You can attach up to 5 Lambda functions to a Kinesis data stream, and AWS Lambda will maintain the different orders and different positions for each function separately. This means that the Lambdas can process different parts of the same stream at the same time. Now, the Lambda code in your function can use any of the popular programming languages, or you can create your own runtime. Now, as I mentioned earlier, DynamoDB's implementation with Kinesis data streams does not maintain item ordering. So in response, DynamoDB includes an attribute on every record in the stream called the approximate creation date time. This is a timestamp accurate to the milliseconds that can be used for item ordering on the client side. It is called approximate, but it's the tightly controlled clock, and it's kind of designed for this use case, so it's pretty good at ordering. It's not perfect, but it's pretty good. Now, one way you can use a timestamp is to find out which version of an item was written first. You can do this by writing the item to S3 through Amazon Kinesis Data Firehose, and then constructing an Amazon Athena query to sort by creation date time. Now, be aware that there is a zero or many delivery of items into Kinesis data streams. In the event that we're unable to replicate an item into Kinesis data streams, we will publish a fail to replicate record count. We will attempt to write items where possible for up to 35 days. After that point, we will stop trying to write the item into the stream. Now, the reason why we may fail to replicate items is because of the payload size limitations in the records for Kinesis data streams. A DynamoDB item, because of the DynamoDB JSON format, could be much larger than the maximum body size for a Kinesis data stream. In the event that it does not fit, it will be dropped and called and marked as failed to replicate record count. I don't believe there's logs for this, but there may be. I haven't heard about them. If there are, certainly on the DynamoDB side, we're not like emitting a metric other than this CloudWatch metric. We're not putting any detailed information into an SNS topic. The item is simply dropped. Now, if you are underscaling your Kinesis data stream, you should be aware of that. You should see some kind of metrics appearing in the stream service, but DynamoDB will also emit a metric called throttled put record count for every single occurrence of an item that it is unable to put due to a throttle. As I mentioned earlier, we will retry for up to 35 days to put the item into the stream. Be sure you're monitoring your streams and they have sufficient capacity. Now, DynamoDB streams, on the other hand, if you use it with AWS Lambda, it can pull the stream service for new records 4 times per second. Similar to Kinesis data streams, all mutated actions will be published into DynamoDB streams. However, unlike KDS, every record will appear exactly once. There will be no dropped records. AWS Lambda service does the same thing as it did with Kinesis data streams, where it pulls the stream on a regular basis, maintains cursors for each shard on your DynamoDB table, and passes a shard's records over to a Lambda function. Now, you can have up to 2 Lambda readers at a time, which is to say 2 readers on a DynamoDB stream at any time. Now, I say at least 2 on the slide because you could potentially get 3, 4, or so on, but somewhere after 2 readers on a DynamoDB stream, you may get throttled. This is because DynamoDB Streams is a multi-tenant service running on SSDs, which have limited capacity. We have the ability to burst above the 2 reader limit, but at some point above 2, you will start to receive throttles, which will slow the delivery of records to your Lambda functions. So for that reason, we suggest you go with 2 Lambda functions. If you need more, you can look at creating a router function, like a message router function. And so it can just pull the record off. When it gets a particular record, it can then go invoke another Lambda function on the side. So it's just, routing functions this way and that to other functions. So A would just route to C, D, and E, and so on. So I should mention that DynamoDB Streams is a completely separate service from Dynamo. So there's no way that your access patterns on the stream service could affect your production DynamoDB table. Now, with the global secondary index, in the same way, if you're reading the global secondary index, there's no way that's going to affect replication into the GSI. But you should know something about how we replicate data. On GSIs, data is replicated asynchronously. Whenever you do your put item operation, we directly store the data and then queue it for asynchronous replication. We provide the response back to you saying it was successfully written, and at some point in the future, the item is copied over. In the event of a provision table, that is usually on the order of hundreds of milliseconds, but it can be longer, especially in the event of uneven access on the GSI, meaning if you have a bad choice for a primary key on the global secondary index, that can create a hotkey, and that hotkey can lead to GSI back pressure. Now, GSI back pressure is a really bad scenario. In the event of GSI back pressure, what this means is you'll get an error back saying, hey, unable to write because insufficient write capacity on your global secondary index. What it actually means is that any item that was written at that time when the buffer to the global secondary index was full, any item will be throttled. All items could even be throttled depending on how long that buffer is full. So this can create an effective brownout where the table could actually accept the write, but because the GSI buffer is full, the throttle will come back. Now the base table doesn't care whether the item was going to go into the global secondary index or not. It just sees buffer full, we need to start throttling. That's called GSI back pressure, and that's a scenario that we want to avoid. We'll talk more about throttles a little bit later on. Now, you can have up to 20 global secondary indexes, and as we'll mention a little bit later when we discuss limits, that is a soft limit, but in general, we see customers use maybe 2, 3, 4, 5 global secondary indexes. It's very rare to see a customer using all of those GSIs and for some reason needing more. When you're adding a global secondary index, there are some things to consider. Now, it is a multi-step process where, from your perspective, you just call update table, you provide the key schema, which are the primary keys of the global secondary indexes, as well as information about the projection. Do you want to include specific attributes? Do you want to include all attributes? Things like that. It starts with the first call. So you call update table, and the index status, if you call describe table, will go to creating. It will also say backfilling a false. And during this process, we're allocating the resources, which is to say we're allocating the partitions, creating what effectively is a DynamoDB table, but you can't see that because GSIs are like DynamoDB tables in that they have table IDs and partitions, but all that's underneath the surface. You don't see that. You just see index, right? So we're going to be adding that, creating that in the background. Tables need partitions where your data sits. Eventually, the resource allocation will be complete, and we will go into the backfilling status. So index status is still creating, backfilling is set to true when you call describe table. At this point, you can update capacity or delete the index, but you can't delete the base table. There's some CloudWatch metrics that you can monitor or to see how far the backfill process is going. Backfill is where we read the table and we look for items that match the primary keys of the global secondary index and copy those into the GSI. Now, one of the most common reasons why customers delete the index at this time is they chose the wrong data types for the GSI. So they will think that their attribute was a number when in fact it was a string. And so the GSI creation during the backfill process will look for items, and if they don't have the correct data type, you'll get an error or it won't be replicated over. However, if the application attempts to write an item and it has the same attribute name as a GSI primary key, but the data type is wrong, it doesn't match the GSI key schema, you will get an error back on your application. So customers will add a GSI, make that mistake, put the wrong data type, get errors back on the application, and then immediately delete them like, oh, dang, I didn't realize that. So be sure that you have the correct primary key data type and, of course, name for your attributes. Now, in CloudWatch, you can monitor these metrics. The online index consumed write capacity, which is the write units used for backfill. The documentation says that the consumed write capacity used by the index backfill or used during the index backfill is actually reported under online index consumed write capacity. So you basically have to switch what you're monitoring and monitor that metric. Now, online index percentage progress is the percent of how far the backfill is completed. So monitor that to know how far along it's going. And then online index throttle events, the number of write throttles. So if you're getting index write throttles, the right thing to do is probably to increase your write capacity because you can still do that during the backfill process, would be the right thing to do. But if you increase the write capacity and it's still not working, and you really want to back out, you of course can't delete the index at any time. Now, once that's complete, the index status will go to active. You can do whatever you want. You can delete the index as you could before. You can delete the table. You can add another index, whatever you want. Be aware you can only add one index at a time. And with that, let's move on and talk about local secondary indexes. Now, local secondary indexes are not worth putting too much time into, but this is best practices, so we're going to have to cover them. Now, why I say this is because a lot of customers can actually model their tables in GSIs, so they don't actually need to use LSIs. So with GSIs, you can create alternate partition keys. Really, any partition key value can be set for your GSI. However, for LSIs, they have the same partition key as your base table, but a different sort key. So if you have a couple different timestamps on your item on the base table, you can create an LSI using the other timestamp, get the data sorted in a different way. Now, you can have up to 5 LSIs. You cannot have any more, and you can only add them on create table when the table was originally created. If you want to remove an LSI, you have to restore the table from backup. So it would be advisable to be careful when adding LSIs because they are limited to 10 gigabytes of data per unique partition key. So if your partition key was device ID and your device ID was like 1234, you could have 10 gigabytes of data on the LSI where the device ID was equal to 1234. Now, it's a common myth that DynamoDB partitions are limited to 10 gigabytes, and this I believe comes from this LSI collection size limit of 10 gigabytes. Now, there's a way to monitor that called return item collection metrics, which I'll show you in the next slide. When you call put item, you can request return item collection metrics, and then you can publish that in a custom metric to CloudWatch, and then keep an eye on, say, what your maximum collection size is. Now, there are some customers who think they might need LSIs. You're more than welcome to add them on table creation. Name the attributes like LSI SK1, LSI SK2, and so on. Do not add them to your items, but later, if you want to start indexing data in there, you can add that attribute to the items, and then boom, they will be copied into the local secondary index. Now, in order to monitor the item collection metrics, is by the way, if you exceed 10 gigabytes, or really technically, sometime after you exceed 10 gigabytes in size of the collection, we will return an error back to you saying you're no longer able to write data. So if you fill up an LSI for a particular item key, you will eventually get an error over 10 gigabytes and you'll no longer be able to write data. So the only thing you can do at that point is to update the items and remove the LSI attribute, thereby de-indexing them, or simply delete items from the base table that you no longer need, thereby removing them from the local secondary index. This is how you do it. You do put item, you return the item collection metrics, and you get an estimated size range in gigabytes between 9 and 10. Like I said, this is approximate. So some customers have contacted us saying, hey, we're seeing an estimated size range of between 15 and 16 gigabytes. And we're like, yes, that's technically true. That can happen. The thing is, over 10 gigabytes, you're eligible to get that error. You don't know when it's going to come, so be sure you're monitoring it. And as soon as you start getting close, consider closing off that collection, creating a new partition key, deleting data, removing the LSI sort key attribute from the items so they're no longer indexed. Think of those things. Now, let's say you're modifying attributes on your LSI. You may be changing the primary key of an LSI. How many capacity units would that consume? How about how many capacity units would that consume for a global secondary index in that case? So imagine you're inserting an item in the base table and you're indexing it. If it's under 1 KB, you're going to be consuming 2 WCUs. 1 WCU for the base table, 1 for the index. Now imagine what you're doing is changing the primary key of the index. So if you had an LSI, the attribute name for that LSI was LSI1 SK, standing for sort key. If you write an item to the base table, changing the value of that maybe timestamp, for example, you have to pay 3 WCUs. 1 on the base table to update the item, 1 on the LSI to delete the old item under the old value of the sort key, the old timestamp, and then the last write, the third one, for inserting the item under the new timestamp. So you have to pay to de-index and re-index the item in the event that you change an attribute that is part of the primary key of the index. And then finally, if you let's say you have a GSI, you have projection type of all, you insert an item and to the base table, you don't change the primary key of the GSI, not GSI1 PK or SK, but instead you change an attribute that's projected into the index, you have to pay to update the item. For this reason, it may be good to change the projection type to included, aka listed attributes, get the list of attributes by name, So the number of items replicated, or the number of attributes replicated is fewer, and the chance that, the probability that you will require a write capacity unit to update the GSI is much lower. Now, be aware with GSIs, when you do a when you do a query, you can only query GSIs or scan them. When you do a query, you only get back the attributes that are projected. Whereas with LSIs, technically, you can get back any attribute, including attributes from the base table, but it's not efficient. With LSIs, if you need an attribute, please project it over. It's not that hard. Now, let's discuss DynamoDB Transactions, both the single item kind and the multi-item kind. This is just a couple of slides, some important things to know. If you're not familiar with multi-item transactions, aka DynamoDB Asset Transactions, which use these two APIs, transact write items, transact get items. By the way, we have Particle. Particle has a separate API called Execute Transactions, which also uses transactions underneath the surface. I will tell you about them. So the transaction operations allow you to operate on up to 100 items at a time. In the event of transact write items, you can do put, update, delete, or condition checks. Those are separate operations, all nested under transact write items. With transact get items, you can get items. You can retrieve items. And in the case of transact write items, these are ACID compliant transactions where we will write all the items to complete all at once or not at all. Now, the paired operation with TWI, transact write items, is TGI, transact get items. With TGI, you are basically making sure that you're getting a consistent view of the items in the event that you might be conflicting with the transact write item. So with the transact write item, if it conflicts with the transact get item, one or both will return an error. But if you do a TGI, you get the response back, you can be rest assured those items were not part of another transaction. You got the most up-to-date value of the attributes. Now, I'm not an expert on transactions API. Some of this honestly confuses me, but the important thing to know is that in each operation that you choose, regardless of which one, it's a two-phase commit, two-phase operation, which means it's going to consume twice as much capacity. You're going to consume, if you're just writing one item with TWI, I don't know why you would, but let's say you were, it's going to be two WCUs, one for the first phase, the other for the second phase. It offers item potency through the client request token. Client request token is either generated automatically by the SDK or something that you can create. And within a 10-minute period, when you make your API operations, the client request token will return an error back if the transaction has already been processed with that token, or if you use the same token but a different request body, which means you miscalculated your token and you duplicated it across different types of requests, it'll return an error back in that case as well. Speaking of errors, here's some things to consider. I summarized everything. Here's all the possible, exception messages you could get back based on which API you're calling. Here's the important thing to know. Even though you may be using put item, update item, delete item, you can get a new exception type called transact conflict exception. So your code must be aware of that. That's really the point of this slide, that the technically the non-multi-item transaction APIs, including the particle options, execute statement, batch execute statement, can conflict with transactions, the write operations. And so your code must be prepared to look for that and then retry those requests. Now, in the event you're using TGI or TWI, of course, you can get transaction canceled exceptions. Those are the event of conflicts with other items where your transactions are overlapping with items in separate transactions, in which case one or both of them will fail depending on what phase, what process, how far we are along in this process. Finally, transaction in progress exceptions can be returned by those two API operations, saying that particular operation is in flight. Now, I would say what is kind of important to know about transactions is that the client request token is super helpful to make sure you have idempotent request. You can just go ahead and send it again. You can monitor any potential transact conflicts by using the transact conflict CloudWatch metric. And that's about that.
Hold on there, Sean. We have to cover service quotas in a different video. It has been an hour, and these people need a break. Seriously though, tune in to part 2 of this series for more in-depth content on security, logging, limits, aka service quotas, and bulk data updates. Thank you for watching.